In the early autumn of 1942, high above the blinding white salt flats of Muroc Dry Lake, California, an aircraft roared into the desert sky. To the ground crews squinting through the desert heat haze, the plane looked entirely wrong. It slid through the air with a strange, high-pitched whistle, a sound utterly alien to anyone who had ever stood near an airfield. And as it banked sharply against the blue horizon, those watching from the dust noticed something even more unsettling. There was no propeller pulling it forward. Yet tied around the nose of that very same aircraft was a carved wooden propeller, strapped on by mechanics under strict military orders. If an unauthorized civilian or a foreign spy happened to look through binoculars, they were supposed to see a conventional airplane. They were meant to believe nothing unusual was happening in the California desert. The pilots flying nearby had even weirder stories to tell. Commercial airliners and army transports flying along the West Coast began reporting sightings that sounded like madness. They swore they saw a twin-engine plane drifting up alongside them, driven by a pilot wearing a bowler hat, smoking a cigar, and wearing a rubber gorilla mask. When the military brushed off these reports as pilot fatigue, the rumors only grew. But the gorilla mask was real. The fake wooden propeller was real. And the secret hiding behind them would dictate the future of global superpower dominance for the next century. America had finally built its first jet fighter, but it was a machine born of absolute desperation, wrapped in extreme secrecy, and racing against a ticking clock that threatened to hand control of the skies to Nazi Germany. To understand how the United States found itself building secret jet engines in converted textile factories and flying fake propeller fighters over the desert, you have to look at the brutal physical reality of aviation in the late 1930s. For 40 years, ever since the Wright brothers lifted off at Kitty Hawk, human flight relied on a single fundamental mechanism, the internal combustion engine turning a propeller. Year after year, engineers pushed that mechanism to its absolute limits. They built bigger engines, added more cylinders, designed superchargers, and reshaped airframes. By 1939, aircraft like the Supermarine Spitfire, the Messerschmitt Bf-109, and the Curtiss P-40 Warhawk were marvels of mechanical engineering. They could fly at speeds exceeding 350 miles per hour. Their engines were masterpieces of high-precision steel, aluminum, and high-octane gasoline. To the average military strategist, it seemed the propeller plane would reign supreme forever. It did not, because behind all that horsepower, an invisible brick wall was waiting, a barrier built into the fundamental physics of fluid dynamics. As a propeller-driven airplane flies faster, the tips of its propeller blades rotate at speeds far higher than the aircraft itself is traveling through the air. As the plane approaches speeds of 400 to 450 miles per hour, those spinning propeller tips begin to reach the speed of sound. When the air passing over the propeller blades hits Mach 1, shock waves form. The air compresses violently. The propeller loses its grip on the air. Instead of pulling the aircraft forward efficiently, the blades begin to stall, churn the air into turbulent vortices, and vibrate violently. Engineers called this aerodynamic wall compressibility. You could add more cylinders to an engine. You could boost the horsepower from 1,000 to 2,000 or even 3,000, but most of that additional power was simply wasted fighting the drag and shock waves generated by the propeller itself. The piston engine was hitting a physical ceiling. No matter how refined the design was, a conventional propeller aircraft was mathematically bounded. It could rarely exceed 450 miles per hour in level flight without running into severe mechanical drag and structural stress. And yet, military strategists knew something terrifying. Speed was life in combat aviation. The fighter that could fly 50 miles per hour faster than its opponent could choose when to attack, when to break away, and how to control the battle. Whoever solved the speed problem would dominate the skies over Europe, Asia, and the oceans between them. In the late 1930s, as the shadows of World War II lengthened across Europe, the world's leading military powers were locked in an invisible technological race. In Germany, brilliant minds like Hans von Ohain were already running radical early experiments with jet propulsion, burning liquid fuel inside a chamber to create a violent expanding gas stream that pushed an aircraft forward by raw reaction force, eliminating the propeller entirely. In Great Britain, a persistent RAF officer named Frank Whittle was fighting his own government's bureaucracy, pouring his personal funds and health into developing a jet engine that could transform aviation. And what about the United States? In the late 1930s, the nation that invented the airplane was dangerously far behind. American military aviation was largely asleep at the wheel regarding jet propulsion. The United States Army Air Corps was focused on building massive fleets of long-range heavy bombers, like the B-17 Flying Fortress, and refining proven piston engines. The consensus among many American military authorities was simple. Jet engines were theoretical, fuel-thirsty, fragile, and years away from practical use. It was a dangerous miscalculation. While American factories focused on building thousands of propeller fighters, secret projects in Europe were quietly making rapid progress. If a foreign power perfected a jet-powered fighter while America remained tied to the propeller, every bomber in the U.S. arsenal could be shot down with impunity. Every American fighter could be run down and destroyed by an enemy that flew 100 miles per hour faster. The clock was ticking, and the United States didn't even realize it was in a race. To understand why the transition from piston engines to jet power was so revolutionary, you have to look inside the machines themselves. A traditional piston engine is a masterpiece of mechanical complexity. Inside, dozens of pistons move up and down, thousands of times a minute. Valves open and close, crankshafts rotate, connecting rods transfer violent explosions into rotational energy, and hundreds of moving parts work together in a delicate mechanical rhythm. If a single valve springs out of alignment, or a single bearing loses lubrication at 3,000 revolutions per minute, the engine destroys itself in seconds. Jet propulsion tossed out almost every piece of that internal movement. At its core, a turbojet engine is elegantly, almost frighteningly simple. Air enters through an intake at the front of the engine. A rotating compressor squeezes that incoming air, raising its pressure dramatically. This compressed air is forced into a combustion chamber, where aviation fuel is continuously sprayed and ignited. The burning fuel expands violently, creating a high-energy gas stream that shoots out toward the back of the engine. Before those exhaust gases escape, they pass through a turbine wheel, forcing it to spin. That turbine is connected by a central shaft to the compressor at the front, keeping the continuous cycle alive. The rest of the expanding exhaust blast rushes out of the tailpipe at extreme velocity, propelling the aircraft forward according to Newton's third law of motion. For every action, there is an equal and opposite reaction. No pistons, no heavy crankshafts, no propellers. Just continuous, rotative, explosive thrust. On paper, it sounded like engineering perfection. But turning that theoretical simplicity into a working combat aircraft was one of the most dangerous and complex challenges in human history. The first major hurdle was metallurgy. The interior of a jet engine's combustion chamber and turbine section reaches temperatures exceeding 1,500 degrees Fahrenheit. The metal turbine blades, spinning at over 15,000 revolutions per minute, experienced centrifugal forces that tried to pull the metal apart at its atomic bonds. If the metal expanded too much from the extreme heat, a phenomenon known as creep, the turbine blades would scrape against the engine casing and shred the entire unit in a fraction of a second. In the early 1940s, the high-temperature alloys needed to survive those conditions barely existed. Early jet engine components failed constantly, melting, snapping, or exploding during bench tests. The second major problem was fuel consumption. Early jet engines were notoriously inefficient, especially at low altitudes. They swallowed aviation fuel at a rate that shocked engineers accustomed to economical piston engines. An early jet fighter could consume its entire internal fuel supply in less than 45 minutes of flight, leaving almost no margin for navigational errors, combat maneuvers, or adverse weather. Finally, there was the issue of engine response. If a pilot in a P-51 Mustang slammed the throttle forward, the supercharged V12 engine responded almost instantly with a surge of power. If a pilot in an early jet slammed the throttle forward, nothing happened for several long, terrifying seconds. Then, as the engine slowly spooled up, it ran a constant risk of overheating, flame out, or compressor stall. A violent reversal of airflow that could tear the engine apart. In April 1941, The reality of this technology hit the United States military with the force of a sudden lightning strike. Major General Henry Hap Arnold, Chief of the U.S. Army Air Forces, traveled to Great Britain to observe British war efforts. While there, high-ranking RAF officials showed Arnold a project hidden under the strictest security clearance in the United Kingdom, the Gloucester E-28/39, an experimental aircraft powered by an early centrifugal flow jet engine designed by Frank Whittle. Arnold stood on an airfield and watched the experimental craft take off without a propeller, accelerating across the sky with a sound he had never heard before. He was stunned. While the American military had been debating the theoretical viability of jet engines, the British had built a working jet prototype that was already flying. And more alarming still, intelligence reports coming out of Europe suggested that Germany was developing its own high-speed jet aircraft. Arnold realized the United States was standing on the edge of a technological abyss. If Britain or Germany perfected this technology while America stood still, the war, and the future of global aviation, would leave the U.S. military stranded in the past. Arnold didn't just ask for information. He acted immediately. He struck a top-secret deal with the British Air Ministry. Britain agreed to hand over complete engineering drawings of Frank Whittle's groundbreaking engine, along with a working prototype engine shipped directly across the Atlantic. In exchange, the United States pledged its vast industrial power to scale up production and build a new fleet of jet-powered combat aircraft. The secret package was loaded onto a vessel and transported across the ocean under heavy armed escort. When that crate arrived on American soil in September 1941, the countdown to America's jet age officially began. But building a jet engine from scratch in a nation that had never produced one was only half the battle. The real question was, who was going to build the secret fighter airframe to carry it? And could they pull off the impossible before the enemy caught on? Before diving into the high-stakes engineering drama of America's first jet, we need to clear up a common historical misconception. If you ask 10 military history enthusiasts to name America's first jet fighter, you might get 3 different answers. Some will tell you it was the Lockheed P-80 Shooting Star. Others might point to the F-86 Sabre. A few aviation purists might mention the experimental Bell XP-59A. The confusion comes down to how we define first. To keep the history clear, we have to distinguish between 4 distinct milestones. America's first jet-powered aircraft prototype, America's first operational jet fighter design, America's first jet fighter to enter mass production, and America's first jet fighter to engage in air-to-air combat. The honor of being America's very first jet-powered aircraft belongs to a machine developed in near-total isolation from the rest of the American aerospace industry, the Bell P-59 Airacomet. The P-59 was the direct result of General Hap Arnold's secret mission to England in 1941. When the British drawings and the Whittle engine arrived in the United States, Arnold needed an American company to build the engine and another to build the airframe. For the engine, Arnold chose General Electric. GE was not an aviation engine company like Pratt & Whitney or Wright Aeronautical. They were chosen because of their extensive experience with high-temperature industrial steam turbines and turbo superchargers. If anyone had the metallurgical knowledge to build turbine blades that wouldn't melt under intense heat, it was GE. General Electric took Whittle's design and reverse-engineered it in absolute secrecy at their plant in Lynn, Massachusetts, designating their version the GIA engine. For the airframe, Arnold made an unconventional choice. Instead of picking major defense giants like Curtiss-Wright, Boeing, or Douglas, he turned to Lawrence "Larry" Bell, the founder of the Bell Aircraft Corporation in Buffalo, New York. Larry Bell and his chief engineer, Harland M. Poyer, were known for unconventional, innovative, and radical aircraft designs. They had built the P-59 Airacomet, a fighter with its engine mounted in the middle of the fuselage behind the pilot, driving the propeller via an extended drive shaft. Bell's factory was relatively small, highly flexible, and, crucial for Arnold's purposes, far away from the prying eyes of major defense corridors. On September 5, 1941, Larry Bell was summoned to a top-secret meeting in Washington, D.C. General Arnold ushered him into a secure room, laid out the British research, and presented Bell with a staggering challenge. design and construct a combat-ready fighter airframe around two of General Electric's secret jet engines. The project was classified top secret, given the code name Project MX-136, and placed under an extreme security shroud. To mask the nature of the project from workers, competing companies, and foreign spies, the USAF assigned the aircraft a misleading designation, the XP-59A. At the time, the letter P stood for Pursuit, the U.S. Army's term for fighter aircraft. The Army Air Forces had previously canceled an unrelated design contract for a twin-engine piston fighter designated the XP-59. By reusing the number 59 and adding the experimental X prefix, military intelligence created a paper trail that made the project look like a run-of-the-mill, conventional piston aircraft development program. Anyone looking through military supply ledgers would see requisitions for P-59 parts and assume the Army was just tinkering with an old, discarded propeller design. Behind closed doors at Bell's Buffalo factory, a hand-picked group of engineers worked behind locked doors with blacked-out windows, surrounded by armed guards. They were building something that had never existed on the American continent. Yet, as the XP-59A took shape, its developers were acutely aware of a frustrating reality. The P-59 was never going to be a world-beating, ultra-high-speed superweapon. Because the technology was so new, Bell's engineers adopted a conservative design approach. They built a heavy, twin-engine aircraft with mid-mounted wings and a conventional tail structure. They were trying to guarantee structural safety rather than pushing aerodynamic boundaries to the extreme limit. As a result, the P-59 Airacomet became America's first jet fighter prototype. But it was not destined to be the high-performance combat jet America desperately needed to dominate the skies. That role would fall to another top-secret project, developing simultaneously in California, the Lockheed P-80 Shooting Star. To understand how America went from a conservative testbed like the P-59 to a high-performance jet force, we first have to look at the secret, high-stress development of the Airacomet itself. In the winter of 1941, inside the Fordon building, a rented, unmarked industrial structure in downtown Buffalo, New York, a small group of American engineers was living a high-stress double life. The windows of the building were painted black. Armed guards stood at every entrance 24 hours a day. Engineers had to show special security badges just to walk between rooms. They were forbidden from telling their wives, families, or closest friends what they were working on. If anyone asked, they were instructed to say they were designing special heating systems for high-altitude bombers. Inside that darkened building, the environment was tense. The team was led by Larry Bell, Chief Engineer Harlan Poyer, and Project Manager Robert Woods. They were working without a blueprint from history. No American company had ever built a jet airframe. There were no textbooks on how to route high-temperature exhaust pipes through an aluminum fuselage without setting the plane on fire. There were no guidelines on how to feed vast quantities of air to twin jet engines without creating chaotic air turbulence inside the intake ducts. Every single component had to be invented from scratch, through trial, error, and intuition. The challenges hit the team almost immediately. The first major crisis was the engine itself. General Electric was working night and day in Massachusetts to scale up Frank Whittle's design, but the GIA engines were agonizingly fragile. The early turbine blades, made from a high-nickel alloy known as Hastelloy B, suffered from thermal expansion under high stress. During static ground tests, engines regularly burst into flames, suffered catastrophic turbine failures, or simply failed to produce the thrust the mathematical models predicted. Each GIA engine generated roughly 1,250 pounds of thrust. To put that into modern perspective, a single engine on a modern F-16 fighter produces over 20,000 pounds of thrust. The early jet engines were weak, incredibly heavy, and swallowed fuel at a terrifying rate. To give the XP-59A enough power to fly like a real fighter, Bell had to use two engines, mounting them side by side in the roots of the lower fuselage beneath the wings. This twin-engine layout created a wide, bulky fuselage that introduced immense aerodynamic drag, the very enemy jet engines were supposed to overcome. As the physical prototype took shape in mid-1942, security reached near-paranoiac levels. When the airframe was completed, it was far too large to be moved out of the Fordon building through standard doors. The team had to break down a brick wall in the middle of the night to haul the fuselage out onto a flatbed trailer. To prevent aerial reconnaissance or curious passers-by from spotting the machine, the aircraft was completely covered in a wooden superstructure and wrapped in a heavy canvas tarpaulin. It looked like a massive, awkward crate of farm equipment sitting on the back of a flatbed truck. The destination for this top-secret crate was thousands of miles away, Muroc Army Airfield, situated on the edge of the remote Mojave Desert in Southern California. Today, that location is known worldwide as Edwards Air Force Base, the legendary home of American aerospace flight testing. But in 1942, Muroc was little more than a desolate expanse of sun-baked salt flats, surrounded by scrub brush, dirt roads, and a few wooden barracks. It was selected for two simple reasons: absolute isolation and miles of flat, dry lakebed where an experienced